Our next talk is by Zhou Feng.
Yeah, thank you very much. Yeah.
About the direction of overlapping self-conformal measures on C.
Yeah. First of all, of course, I want to appreciate this opportunity to speak in this beautiful city and institute. And I like this format. And today I'm going to talk about the dimension for self-conformal measures on the complex plane, especially when the effects are overlap. This is a joint work with Ariel Rapaport. So this gentleman has other obligations, so people are not joining our discussion this afternoon, but I will be the front reporter for him. Yeah, if you have some very interesting comments, questions, are welcome. Okay, set up. Okay, was set up on notations, and I don't want to explain more background because Ismail has to do a great job for me. So set up. So find the homomorphic FS by I on bounded domain omega subset of C. And require FS a number of maps is finite, and phi I, each phi I is homomorphic. And injection on a domain applying contains omega, and we require these contractions. The IFS requires contractions, and some self maps, phi I, omega closure, omega, and derivatives I the norm is between 0 and 1, and Z in the closure. And you realize that this strictly assumptions hyperbolic assumption plus this regularity assumption, you give the bounded distortion. This is very important for us. And then we have a positive vector P indexed by the same alphabet, and we without the generality, PI are positive vector. With these two data, you have the unique that exists in some cases. I rather together, therefore conformal measure. We use mu is the push forward of this beta. Beta is the ballooning measure on the symbolic space, and set K push the image of the full symbolic set, and its support, because I assume it's positive support of mu, and they are self-conformal, means mu equals phi I mu I equation by phi. Okay, so this is our setup, and now we can state our main theorem, and we. Sorry, I remove all the background of important works starting from Hoffman, Rapaport, Jude, and Schmucking, and Hoffman from Yaga, and yeah.
What do you make any assumptions on omega? Like, is it convex or
convex domain? About the bounded domain, between the bounded, open, and connected, no convex. Okay, no convex. Yeah. Thank you. My theorem says suppose first phi does not preserve point or any analytical curve that is closed in omega relatively, so closing the relative topology, and 2 phi is not homomorphically conjugate to a homozygotic IFS. 3 y is exponentially separated. Then we have the dimension mu equal attains the natural upper bound, which is expressed as the dimension, which is the decreasing rate of mass, and the other exponent, which is the decreasing rate of diameter, and 2 is the ambient dimension. Okay, so this is our major theorem. I would like to make some remarks. If you, okay, I don't think everybody was in Procureur, so I can explain the necessity of these assumptions. The first is a necessary because if preserve means you have preserve means the phi E contain E. So, for example, if the point, then phi preserve a point, a common fixed point, the dimension is 0. You can make this symbolic upper bound to be at least passive, and this is the obstruction you have to destroy. And if you preserve an analytic curve, for example, this is your omega, and you have a curve, and then the dimension is 1, but the dimension, this is geometrical dimension is 1, and then upper bound can be easy to make it to be bigger than 1. And this is necessary. And the second assumption is essentially necessary because there's a phenomenon traced back to Hoffman in the self-similar case, which means this kind of geometric configuration. You have a bunch of lines sitting on a candle set. This candle set dimension of this candle set is strictly less than 1, and the fiber dimension of fiber is 1. So if your angle preserve, if self-similarly preserve very straight, a bunch of straight lines, and then the dimension geometrically, because of this geometrical obstruction, dimension is always strictly less than dimension of this plus 1. But you can easily make this natural upper bound to be 2. So the less than 1 plus 1 is strictly less than 2. So this is also a obstruction. So this is essentially you have to remove, and the third is exponential.
But can't you remove it by adding irrational rotation? That you assume that this argument is irrational and behaves irrational.
Yeah. Thanks for the question. That was a sufficient condition to achieve the signal goal. To assume some kind of irreducibility to destroy this phenomenon. So this is a very good comment, because you can have even more checkable condition. This is not so checkable from the appearance, but you have some more checkable condition. But that was corollary. Today, as the title said, is a focus optional. So I want to explain the idea of both. This is main theorem, and this exponential separation has already appeared in the talk of Eastman, and I don't have to define, right? Maybe I should define.
Is it exponential separation or strong?
Exponential separation.
So the weak.
You allow many overlaps. That's why the title is the overlapping. Yeah. Before people are just study this separated case. Yeah. So it's mine. And what's next? So this upper bound is just if you define a norm of the mass by u and minus phi v, u v distinct with thickness n, and the norm is the supernorm of this function is greater than small numbers n, c to the n, and n don't have to be all large n, infinite n, that's enough. Infinite many n, and this is positive. This is the exponential separation. Okay, this is basically the main theorem, and I would like to make a further remark. Okay.
I'm sorry. So for the first assumption, what's the point of specifying the curve has to be closed in O?
Okay, this is no. You think logically. You impose more assumption to a curve, which means that you make your assumption weaker. You do not preserve these kind of special curves.
Yeah. So you're saying that you're allowing yourself.
Yeah. This, for example, here. For example, your curve touch the boundary.
Yeah.
It's not closed in the complex plane, but it's closed in the omega. Your curve can touch the boundary.
So you're allowing your system to preserve some weird analytic term which is not closed.
So so that's a bunch of family of curves that you want to not preserve. The more special, you preserve the next more special curves, which means the assumption is weaker.
Okay.
Yeah. So the higher regularity you impose on this assumption, which means your assumption is weaker. Yeah. And also, this homostatic is weaker than the self-similar. Because the obvious reason you want to include the example of Sierpinski triangle, right? Okay, Sierpinski triangle, the obvious address is no rotation, but you can do a rotation by pi over 3, and then you manually add some rotation is still satisfy all the assumptions. So, yeah, it's not a homostatic. And I think do a comparison to your assumption is weaker because you want to say do not contribute to a linear address. This homostatic is more special than linear, so it's also weaker than not linear. Okay, yeah. The remark I want to make is related to other field. This is a very high level analysis. You can think of, if you are familiar with rational type of rigidity in the homogeneous dynamics, you can think of these two assumptions at the orbital under some closed prober subgroup. So anyhow, this is a big rigidity program, and this is in our field, in our dimension field. This is a dimension field analog. Anyhow, that's a very vague stuff. If you haven't heard of this kind of rigidity, forget it. Because good math should be concrete and precise. And learn the concrete from the dream and learn the precisely from Ariel. Yeah. Okay, let's go to the proof. Can you move the camera? Yeah. So the proof conceptually divided into two parts. The first part, I would like to give a big picture why we needed some kind of called entropy increase. So the first part I call it a reduction to the entropy increase, and the second part I focus on the explaining how to prove at least a waving hand, or I should provide enough details how to prove this entropy increase. In short, is two entropy increase and the own entropy increase. Now we will focus on the reduction to entropy increase. Entropy increase, I would say in our setting is under some non-linear action under polynomial action, and is not just on C. C is two-dimensional. There's more obstruction for the entropy increase. So you warm up this.
Okay, can I just one more thing? Just I'm trying to understand the statement exactly. So homothetic means you don't have any rotation.
Yes.
So are you also saying something about self-similar IFSs? Like, does there also say something about self-similar IFSs which are not?
This is perfectly applied to self-similar IFS. I don't see it, but self-similar IFS is a special case of our case.
So there's something new in your theory, but even for some self-similar IFSs which are not conjugate to homothetic.
We'll say the self-similar has already done by Mike.
So that follows.
Yeah. So it's a extension of Mike's result to the non-linear world. And in the plan, yeah, maybe I should make another remark that Mike's result in RD. So this I think we discussed whether we should include also the higher dimension case. But in higher dimension case, the conformal method is finite dimension, is Mobius transformation. So in even higher dimension, the difficulty are reduced. So most interesting case is the plan and also in the plan there's the anti-homomorphic is also not so elegant. So we focus on this case. So you have all the difficulties you are encounter. Infinite dimensional Hawking space is a homological on this omega and also this high dimensional phenomenon. Yeah. Okay. Yeah. Any more questions, comments? Yeah. Oh, okay. Now okay. We recall this warm up theorem of Mike. So that mu be self-similar on R, and this is in the 2014 for any m greater than 1, the dimension of mu. I don't have to define the dimension, right? You can define the exact dimensionality by the inform and the Wu, and all this kind of packing dimension, upper and lower, and Hausdorff upper and lower, they are coincide, but not like Q stuff. If you only care about typical stuff, yeah. Minimum in through and goes to infinity, and entropy of this measure, this atomic measure, I will define, and the partition increase from n to n times n divided by n, and this one is the ambient dimension, and well, this new n equals to the 2 to the minus n atomic approximation of mu. More precisely, so this is the more intuitively, more precisely, nu n equals to u in n. I will define this is very common to us, just some section such as the single set has the comparable diameter is pi, and the direct measure by u of 0, translation part of pu. I believe this notation very familiar, right? Pu and phi u, I don't have to explain that. And phi 0 just the translation. So IN just we use many times in the at least in the textbook of Fractal. So IN equals to words. So this is my notation IN, and I want to say phi prime u. So it's linear, so it's independent of points. So and 0, and it's less or equivalent to the minus n, and phi u minus phi 0, and that's it. This is a usual partition. Usual partition of a symbolic space. The advantage is that if you choose this kind of words map to the functions, the diameter is 2 to the minus n up to a constant z. And I'll draw a picture. Okay, I think this is the statement of the theorem. And I would like to make some remarks. So this is your dimension you want to study. If there's no m, it's just the exact dimensionality. You know this is equal. This will also dimension mu equals to limit n goes to infinity nu n d, and this is just the exact dimension. More than exact dimension, a little bit different is that this nu n are atomic, but the approximation is level 2 to the minus n. So according to this partition, the error is diminished. So this you can replace this mu N to mu. This is the consequence of let's say young that from exact dimension you get entropy dimension exists and equal this quantity, but this equal because this is approximation at the right scale. So originally from exact dimension you get this formula, but the minus result tells you that you can increase. You can change the camera. Increase the scale n by n linear on the exponent part, which means super exponentially. The partition is finite, but still you get this equality. And the example, maybe I should write out mark. If phi exponential separated and choose m depending on the exponential constant m large, then this becomes entropy over chi. And if phi algebraic, which means the quantity parameter algebraic, then this quantity it becomes random walk entropy over chi. Minimum. It means the right hand side. Right hand side equals to minimum entropy chi 1. Okay, this is the remark. So this recovers the result, and then I explain the proof. Based on if you assume the entropy increase, how to prove this result from this? Okay, I can erase the remarks, and this is just the canonical definition, and I draw a picture for you. You have a better eraser. I don't think this eraser is very nice.
You can use the spray. It makes it a little bit better.
Ah.
No, the spray.
Yes.
Yeah. It makes it better or worse. These are the two.
Yeah. I do not recommend taking notes. Take pictures or focus on the listening.
I mean, that chip is exponential separation condition, right?
No. I tell you the remarks. There's no assumption. Just increasing your scale. Do not still have a formula. Then you increasing your partition fine enough to see all the atoms. One atom in each one atom of atomic measure in each atom of the partition. Then you make sure this becomes the computable natural law. Yeah. There's no assumption. It's actually something and R. Okay? Yeah.
So you mean that so with exponential separation condition, then you can choose suitable m and such as your limit duties entropy factor.
So I remark here that if your FF and some exponential separation or weak diagonal property, this quantity becomes computable, more computable. For example, entropy, Shannon entropy over chi, if it's an exponential separation, if it's a weakly diagonal, then this becomes a random walk entropy over chi. So this is a Hoffman result. Yeah. And then you draw pictures. This is the mu, and you have this FS. Let's say, so diameter, let's say this is 2 to the minus n, and diameter 2 to the minus n, And new one, let's say it's homogeneous, just for the idea. New one just blue first. Well, yeah. So new one is this left hand points. And weight is PU. For each single cell, you have some weight. So the new, so that's why we call it a 2N approximation, because the error, the resolution is 2 to the minus n. So this is scale 2 to the minus n, and we prove this by contradiction. Proof by contradiction. Assuming Hoffman's entropy increase, and we abbreviated. Okay, this is the key observation. Trace back to Mike. Rough idea is that okay, if you have a dimension draw, this is scale 2 to the minus n, then you further refine your scale. 2 to the minus, so this is 2 to the minus mn. You will see if you have this. Okay. For this dimension drop, you just distill a positive proportion of these atoms, such that the entropy of this part respect to this higher partition has a positive entropy. Then you acting on your measure, on a very nice measure. For example, self-similar has a dimension drop. Then you are increase a little bit, substantially. This is the entropy increase. So that doesn't mean write it precisely. Remember, precisely the way for Ariel. So okay. Let me give you some parameter first. So epsilon, delta, and there's some even smaller, and there's n large, and you require this some constant depending on this mu, which means trace back to phi and p, and this epsilon. So by contradiction, which means if there's a dimension drop, you want to get a contradiction. This is a proof by contradiction, which means suppose on the contrary, dimension mu, so less than the minimum, so less than two separated quantity, and the dimension mu is less than limit soup and infinity, and nu d m n n. So this is the counterpartial assumption, and you can assume this epsilon is here, and yeah, and this is the notation of this is n. So I think that from the symbol you can tell that the epsilon, delta, and eta are positive numbers from between 0 and 1, and n is an integer. From notation is self-expressive, and this notation means large. So this is small. If it doesn't minus, it's small, and yeah, that's a notation, very convenient notation to see the dependency of parameters. Okay, so. And then I can write the argument. I want to keep this, but okay. I write it in this way. So you have the eta is small, is arrow, and n is large enough. Mu plus eta is greater than -1. Mu e M N D N. This is correct. Yes. This is right. So this is just by exact dimensionality. Because as n large enough, this is two scale, M and N. This goes to M minus 1 times the dimension for mu. And now I normalize by this M minus 1, this is the right scale. Yeah. And I write this as I use the subsimilarity. This equals to nu n convolve. This convolution translation S to the minus n. Say maybe in real case maybe there's some error, but for idea safety, you have to this is a mu d m n n. Okay. And then I can do things by, so this is a similarity. And this is a picture of this new convolve this smaller pieces. So this is 2 minus n mu, each of this. Okay, and then what do I want? I want to destroy, not destroy, to distill positive measure part. So I use concavity. So I use concavity, nu n equals to nu and d and dn, the scale of n, dn x d nu n x. This is my notation. Any measure, this notation is nu restrict m and normalized by f. So this is just write nu n, right? This is nu n, and the sum of this. So the red partition, the scale is 2 to the minus n, and the blue partition is 2 to the minus n. So you write this as this expression. Okay. And any problem of this? No. Yeah. That is really nice. Entropy is our friend. The concavity is our friend. We can expand and do not decrease too much entropy. U n d n x. Oh, in the real line, I can use x. So, convolve x minus n nu d m n d n, and that integral nu n x. Okay, this is the concavity. As I said, what's next? What's next is we want to decompose this integral domain. Maybe I can do an additional step by zoom out, because the diameter is too small. I want to zoom out to get rid of this part. So next step, I zoom out to normalize the diameter of this part and this part by scaling by times 2 to the n, normalize zoom out. This is R, and this is the minus 1 n mu s to n nu n d n s. Remind me if I made some typos. Any problem of this part? No. and this is D, M. Oh, I forgot the mu part. Got both mu and D minus 1 N D nu N X and minus some error. Some error like this. Because you can do that. Yeah. And you see you expanding by here. So you can expanding as expand the partition and measure together. This part becomes the diameter like 1, but you expand the diameter of this measure is also like a constant. So you let n super large, then the conditional part goes into this arrow, and this partition, this is more interesting, separating the partition, decreasing by 1, because you expand by n, and this cancel, and this as a relative. Okay, so I write this as nu and x. Okay, this is the format we want to do things. And then we can divide them. We can write this as 2 parts. F plus F complement. I'll define what is F and what is the not F.
Make sure you erase with the black part, the other.
Yeah.
That's the part which erase as well. Just when you're using the eraser.
Yeah. Oh, yeah, that's why I did.
Yeah.
Okay, I take back my comment. Sorry. So I should make this clear. This is the mouth, and this is separated domain. And I define what is this domain F. F is the X in R such that mu theta X, the entropy at this scale, entropy U n theta X D minus 1 n is positive by some epsilon. Okay, is larger than n, because there's some divided by m, so that epsilon should depend on n. But anyway, m is fixed first. Yeah. So epsilon. Okay. So this is the part of the point, part of this action. We can think as this action on this measure. This is F is a part of action measures, active measures with positive entropy or positive energy, actually doing things, and they're not just doing nothing, not so atomic. They are positive entropy. So we can separate these 2 parts. This is where we use this entropy increase. On F, we know this active measure has a positive entropy, and we know this mu is similar. Similar means uniform entropy dimension, and in the real line, and the other, I believe for Max has already proved entropy increase. Well, no, uniform entropy dimension, and it's not a full dimension, so we can apply entropy increase on F. Remember there are 2 parts, active measure, positive entropy. And the base measure, very nice. And there's room to increase at the real line. So we can, on this part, we get some increase by that. So, and the remaining part, remember, this convolution is a smoothing action. And so I leave the other part at least there's a lower bound by the dimension. If you look at this Photoshop, right, you conform that if there's a dot of that, you blur it, then very smooth. This is the computer science use convolutions. Yeah, convolutions is the smoothing action. Smoothing action. So on that part, you have the increase. You increase. So this kind of increase. In mu plus delta, and the domain is new NF measure. Okay, that's the part I didn't explain, but it's very important because I want to destroy distill positive measure here. And this new F will complement at least d mu minus some O eta error and the minus O at measure error. Okay, is there any problem? This is the entropy increase. Statistically, is entropy increase apply on this part. Okay. So where did we use this? I remind you, you want to distill a positive proportion of this active measure and positive entropy. This comes from this. This comes from this assumption. You can write because there's a n-1, you can write this as an integral format, and there's a gap. We have the epsilon man, and you use this is the upper boundary by some m, and you can get a new NF is positive with the epsilon, or some other epsilon 0 depending on epsilon, and so if some epsilon 0 depending on epsilon. Anyhow, if epsilon is a gap, if epsilon given, then you can using some integral format and using some Markov inequality, you get a new NF is positive. Then epsilon 0, epsilon 0, maybe I should write this place, depending on epsilon. Okay, then we are finished the contradiction. This greater or equal than this part and this part combined together, just dimension. Oh, I should use black. So this is dimension mu, and plus this is as a epsilon 0 times this delta, and the remaining part, this is less than 1. And the remaining part can be controlled by constant times n. So this is the epsilon 0 times delta. This epsilon 0 only depends on epsilon, and do not depend on atom, and divide minus n. Okay. So this is a contradiction. Why? Because this is your left-hand side. This is your right-hand side. And this dimension can be cancelled out, can be removed. And what's remaining? You get epsilon 0 delta is less or equal to O eta. But our assumptions that eta is super small compared to all the previous parameters. So this is a contradiction. I hope this convinces you the idea of entropy increase. You can distill positive proportion of active measure, and you acting on some very nice measure with a room to increase. For example, some similar with dimension draw. No, dimension draw is not full dimension. Okay, this is basically proof under the assumption of entropy increase, performance entropy increase. Entropy increase is just a direct corollary of Hoffman's inverse theorem. Hoffman's inverse theorem tells you statistically in spatial and in scale, the open with obstruction are the only obstruction for entropy increase. And this is the direct corollary of Hohmann inverse theorem. Okay, and then I don't think I think I have explained too much detail, right? Because the title is focused. How much time do I have?
About 40 minutes.
40 minutes. Okay. Then what the next I want to do?
Sorry, could you say explain why F has positive dimension, how it follows from the second inequality here?
Yes.
I realize you want to move on. Could you just say something?
Yeah, sure. So this agree. Disagree, because this is the approximation of this new mu.
Yes.
Yeah, you can see that the new n just okay. If you replace the new n as mu, it's just exact dimensionality, and I replace this as dimension mu plus some very small error eta, and I put this eta in its distribution. If you are more satisfied, you count this. Okay. Okay, then what do? You can move this distribution to left hand side, and you move this to right hand side. You got this. Because this is the strictly refined, so you can write it like the integral format.
Yeah.
Okay, then this is upper bounded by a constant depending on n. And then you get by Markov inequality, you get a positive summation 0. You can even make an infinite 0 effective.
Thanks, sir.
Yeah, cool. Yeah, and then maybe I don't have enough time to explain the okay, I can make a further remark. The reason I leave this is that there's a magic. I would say. It's later remarked by Hausdorff in 19, such that for any q positive than 1, the q dimension equals to this. This is Pavlov's proof, Pavlov's major theorem regarding of course, his ultimate goal is not the dimension of self-conformal measure, but his major application in the dimension theory of self-conformal measure is like this. So his entropy, so for him, the entropy increase means his name is FQ flattening. So this part, okay, this argument part, they all trace back to Mike. And I think I'm justified to make a comment that this part is the same. Because I got a confirmation from Pavlov himself when I gave a talk in your scale. I think Amna was there, right? He gave a confirmation, yeah. But this entropy increase part use a different proof, different idea with the Bogan and what BSG is that Bogan summary goals. Okay.
So just one question. So it's this version what you stated.
Oh, explain. I didn't define it clearly.
You didn't define it clearly because the HQ is assumed the HQ entropy, this HQ formula summing up for the to the power Q and whatever. So this particular version, it's not stated in Pavlov's paper, but this is true for that version. But us, it is on the board. Just
change the expression. I like this part because two reasons. I like entropy more than Q norms.
Yeah.
Entropy. So you can call Pavlov's Q flattening as Wrongian Q entropy increase. I mean Wrongian student. Now I make the connection to Wrongian. So this is the wrong Q and P increase. As in this Kakayan world, you have this Q flattening stuff.
And now you are going to define it precisely.
Yeah, precisely. Precisely. Okay, this part has the same in the IQ world. This is confirmed by Pablo himself. Okay. Okay, I will make a remark. So remark. IQ world. Okay, I've already defined this IQ dimension. The geometrical dimension is just the increasing rate of this Q entropy mu in respect to n dn, and well, this HQ is I will write wrong wrong Q entropy. For any measure, we measure theta with respect to the partition equals to Q minus 1 minus summation D in the dimension and C D Q out Q. So sometimes they call this as IQ. No, I will not call it normal IQ sum because there's no one over Q sum. So they deal with this quantity more often. In my experience, the reason is that they change the order for summation and mode. So maybe this is more convenient. Oh, okay, this is the definition. There's something unclear? No, right? Okay, the existence is by Paris Soviet. I think so, right? Yeah. For the existence of Q positive. Yeah, this here we will choose the positive one. So this is clearly the statement in the LQ word. Okay. Now maybe I should okay. I think I don't have to okay, how much time do I have?
Half an hour each.
Okay, cool. And then I can find it. Okay. Now I said the entropy increase theorem for us. There are one important. So my original plan to write all the arguments in the nonlinear order and the polynomial stuff. And then I would like to emphasize I was state the entropy increase for us. And then I emphasize one key input is Ariel Rapaport's technique of Taylor approximation from the homomorphic actions to the polynomial actions. So now I say that the entropy increase for polynomial actions on plane. Oh. Now you understand the importance of entropy increase, right? The role of entropy increase. Somehow you have increase. So. This is the theorem we need. Entropy increase. Not LQ entropy, the normal Shannon entropy, partition entropy for polynomial actions on C. suppose. Oh, so actually in reason we only for the practical purpose, we only for the base measure is our self-conformal measure. So suppose this self-conformal measure dimension is not 2. We suppose this is 1 and 2. Remember, okay, recall 1 and 2 are just it's not a preserved point of any curve. 2 is it's not a homostatic, homomorphic conjugate of homostatic FS. Then for any each node, 0, 1 and k in integer, k is the degree of polynomial, and for n is the scale such that maybe with each node, no, sorry, I forgot the increase part. That exists the delta depending each node k positive such that for any scale then in with each node k n large. And then that some active measure nu in active measure measure on polynomials is polynomials degree that over the k. Okay, this polynomial this is finite dimensional complex coefficient. In the real dimension is 2k plus 1. 2 bracket of k plus 1. And new active measure, we want somehow is also we recall we also do now that you make sure that meter is right. So new so that L2 norm is therefore bounded by some each node. For any f in the slope of this active measure nu, and the L2 norm, because I said you can identify this as the real okay, you have the L2 norm. And this I want you at least you this is no linear action. You don't want to this f compact too much. The derivative z is a low bounded by each node for any f in mu. And this space measure, I would say I can require this any z in the unit ball. My active measure will be my active measure to be but my basic measure will be supported on these unities, open unities. This is open unit, this is standard notation. So I don't have to explain. Oh, and for any cosine is some arbitrary normalization. This is some innocent distortion, controlled distortion. After you zoom out, remember from here and here, zoom out, right? In the linear part, it's very clean. But in the non-linear case, there's something remains. This is the cosine in this F, FC. C is a constant depending on the phi and p. So something. This is some G from domain. Without also generality, you can think about your domain like this. Okay, it doesn't have to be complex. And this is a unit ball. Open unit ball is omega. Okay, because you can make this assumption. Maybe in your fancy notation you have this. So this is the without those of generality by composing a homostatic, contracting homostatic, you can conjugate and make this assumption. And so that's why I can assume any Z and D, G homomorphic injection, and the derivative is bounded by pinched, I would say, pinched for any Z in omega queen. This is something remain after you zoom out. This is some innocent distortion, see? Innocent distortion. This is happening in nonlinear world. And for the else, if mu n partition n, so this partition in this polynomial space. Polynomial space is this finite Euclidean space. This partition positive. Then after our action, why that's n? No. In the application, that's on acting on our measure, and dn will increase. So in higher scale n, this will be the entropy. That's why it's called entropy increase by delta. And see whether there's some mistakes. So this is partition in C. Right? Okay, that's one clear stuff. So this is my statement. I will explain this precisely. Acting, okay, you have some space X, you have some action, some map, new, and this some space Y. So in the map, supposing on the measure, on the map from X to Y, you can check all the measurability. This you have some measure mu here, and the new in the action, new acting new equals to the push forward of the product measure new, okay, in blah blah. That are all standard notation new of under evaluation map. Under the map, X F maps to M X. So you have all the measurability in the real case. You have this continuity, you have the measurability, all the things are well defined. This is the meaning of action. And if X is a semigroup, then X acting on itself by left translation, then new this normal convolution equals to new dot mu. So and new and mu are all supported on X dots. So this is the definition. In particular, if X is a Euclidean space for a abelian group, Euclidean space, this is the usual translational convolution.
And the other last time maybe acting on the side. Acting
on that side, yes.
Acting on.
Yes, side. This is allows us as some freedom, because in the previous in the case, in every small pieces you have something remain. So in the real case, this two sides are depending on the small words, small single set. But you have the uniformness because you have defined this for all the sets.
So should this be? So you have the broad side of what it is. So should it be if this positive, then I guess it's the delta depending on.
Delta depending on each one.
Okay, so if you have an epsilon entropy, then
you increase
the sign you push forwards will get a delta increase for any sign.
Yeah, for every sign in this collection of functions. This collection of functions are homomorphic from the domain to the unit ball, and they are homomorphic injection and bounded distortion.
And the C, what's the quantifier on the C, the constant FC?
C is just any, okay, in the real case, this C depending bounded distortion constant. Yeah. And I'm writing the P here because you need this N large enough. Okay, I write C here. The C depending on phi, make a C large enough to replace the entropy by dimension. Because you exact dimensionality, you need a large enough to relate the entropy rate to the dimension. So I write this as dimension. This is the format we need. And the argument, so the key technical argument here, I write it as polynomials, the acting measure on the polynomials. So from the homomorphic to the polynomials, this technique was due to Ariel. And the remaining argument, the essence, I was the essence traced back to Mike, and some cleaner and more strict, more clean argument has some shadow in the book, paper for Hoffman Rapaport regarding the dimension of planar overlapping self-conformal measure. Okay. That's the entropy increase we need. Okay, and now I finished my first part. I promised you. The second part is on the entropy increase. This is to the entropy increase. How much time do I have?
20 minutes.
20 minutes. I think I can prove by waving hands. Is you already enough, I think. Okay, any problem regarding this entropy increase?
Maybe just what should the bottom line now be exactly? So if the psi mu is just the psi, the action of mu on psi.
So this is the push forward of mu.
Right.
Yeah, right. Yeah. Yeah. So yeah. Yeah. So that's it. There's some. So in the world of random walks, they usually change the notation from mu and mu, because I think for them mu is used more often. But for us, we study this limit measure, this similar self-conformal distinction measure often, so we use this mu as the base measure. But then they change the role because they want to driving measure involved understanding this average operator, this is the mu and the yeah. Okay. There's some question from the audience in online, no? Yeah.
Why do they need that this time?
What?
Why do you need that this time?
I told you when you action, this is our base measure. Here you change the f part and f complement part. This is remains in the linear case is S2n minus n and new composition is equals to u, right? In the actual case, this is some. This is phi, this signal measure v mu and renormalize composite. Okay, in the push forward line, and some new. So this is very small phi mu v, and then you normalize to some measure like this by this psi depending on nu. This is the measure psi you want to apply. And this nu can change because you have many different symmetries. So you need some uniform. Okay? Yeah. I hope you. Yeah. Then I got 50 minutes left. 50 minutes. Okay. On the entropy increase. The method strategy is using linearization and then to apply Hoffman's entropy increase. Entropy increase. Here R2 and here's the result for RD on C. Yeah. And what is the linearization? Linearization already appears in the paper of Hoffman in 2017, and the first appearance of this method in our field is the paper of Hoffman and Miak, and also applied in the paper of Balash, Barani, Hoffman, and Rapaport. And I believe also in the later, maybe you'll find out all the nonlinear stuff. And yeah, for the linearization, I would say a few of the key. The key is okay, you want to get an entropy increase. Maybe I don't want to write the key. Key is in the paper. Yeah, the key is divided into the smaller part and using local global and then divide the smaller part, and you can transfer this action convolution by your action on a point and scale by a derivative of mapping your actions. That's the linearization. The advantage is the concavity and the local global property of entropy. Yeah, that's the key linearization. Now I focus on the entropy increase. Entropy increase in the plane. So enemies for entropy increase in RD, I'll say it's just one situation. For systematically, I would say this is the new C, and some measures supported on this V is the subspace IRD, and this mu theta is like this. Theta is like this. Theta some kind of saturation. Saturation means you have some space P, and the measure on these fibers are saturated. Saturated in terms of entropy is very close to full entropy. What I mentioned, very full. And C is like this. These two directions are parallel. So when you acting by translation, or Hoffman's attribute for translation, you acting this probability measure to this measure, you move to this part, but it's saturated. So cannot increase. This is basically the trivial phenomenon in cannot entropy increase. So more precisely, if V equals to 0 part and zero space trivial, and this is 0, and you which means C you are control supporting at one point, C will become impaired with some small dot atom. It's not atomic, but some small measure support close to concentrated at one point. But when with the 0, then there's no much information for this theta. And if V is some line, let's say on R2. R2. Oh no. Real projected line. And then this becomes this is the right picture for theta and new theta and theta. For entropy increase under C theta. And if V equals to R2, which means the saturation. Okay, if V is R2, which means this is just a full plane, the saturation means saturation, then the counting of R2 is 0, and you can. Okay, it's not. It's not common. So you said a planar measure saturated, not saturated, concentrated on plane is saying nothing. So for the active measure is nothing. For the plane, for the this base measure, for the saturation, which translated to very uniform. This is basically the phenomenon in the plane. The plane, 3 different cases depending on what it will be. In particular, if it is a real line, okay, then there's not this case. This is just Hoffman's entropy increase on a real line. There these 2 cases. I remember if you listen to the talk of online, then there's something like a tree, like this phenomenon, this kind of stuff. Okay. How much time you have?
10 minutes.
10 minutes, okay. So, Hoffman's theorem, Hoffman's inverse theorem for translation convolution for Xiang partition entropy or RD. Okay, so it's similar. The gist is that this in the one scale phenomenon, one scale enemy, one scale obstruction is basically only obstruction you will see according positions and scales. So for any additional positive in case and some window and some scale n with additional. Yes, this is the random dependency, and this is the window. This is the arrow, the resolution, and this is the scale or the full scale, and then that some measure c and theta in the space in the measure, the probability measure. I will use I said this for distribution, and this is for measure. Okay, distribution was my distribution is a measure of measure. So this is the measure, and this is the 4 on RE. For simplicity, just center at 0 and 1 and close ball. Since something this notation is clear, the diameter is controlled, and this such that the entropy at the scale n and on the convolution is not increased. I forgot the important stuff again. That's the delta positive for n depending on these 2. And if the entropy do not increase by very small delta depending on epsilon, then okay, the saturation is basically what you see. Then there is this linear subspace V1 to Vn subspace Rd such that okay, then you see according to scales and two positions Un cross nu. So nu and V is very okay. Product measure. I put the base measure first. No, I didn't use mu and V. x, y in scale. This is my notation from 1 to n. It's very standard. D, such that, okay, this is the basically what we will see. Okay, I saved this picture like this. So this okay, this is the counting measure. The also self-work is expressive is equals to summation delta I weighted over I. It's a counting measure, uniform counting measure. And this is the basic measure. This is the base measure. This is the active measure. This is the y, not atom. If such that the situation, okay, situation, this should be saturated, and this should be concentrated. Saturated, this is a picture. I want to make it precise. Precise means the entropy is very close to full. How do I express this? Which means original measure. Expression new. Okay, in the z, x, and scale I. This means theta. This is di x. This is the diagonal partition. This is atom containing x. Restrict and normalize. And I and D scale from I and oh sorry, this is the window. This is the window. The n is a long scale. Okay, this is the n, and my window is m. My window m, and I didn't normalize. If you put this to this, then you can remove this. This is scale minus the projected P projected in this group. Okay. V and theta x I d I plus m is full with 1 minus epsilon.
VI.
What
I mean VI. The direction is VI. You have the right.
yeah, yeah.
And the dimension of the right? The mode velocity.
Yeah, in the plane, yeah.
Then you write RP.
And this concentrate VI C Y I scale I M is smaller than epsilon. And together, this is the N is larger than 1 minus epsilon. This is basically the statement. Statement said in statistically, according to scale and the location of opportunity to measure, of this small error, this saturation, this phenomenon, basically the obstruction you have. And then for how to prove entropy increase, you destroy this phenomenon. If you destroy this phenomenon in the plane, okay, now in the plane, C, and then for C, you want to destroy this because in the plane that's 0 and the line and the full. For 0, which means you want to destroy that the active measure is very small in some sense. This small can be verified by active measure as positive and epsilon. Of course, this is the P. So this is the so this can be deduced by your assumption, but by as you can see in the plan, this is by your assumption that dimension 12 prove contradiction, dimension draw, and some separation, because now is if I write this, okay, write this, okay, now I'm explaining in the final argument. Now you can just suppose this is some measure on the polynomials. Then you don't have this final argument how to deduce this passive entropy. So you destroy the first phenomenon is new and arbitrary. You destroy this by some this. This is in total scale n is positive. Then you can see that a positive scale. This cannot happen. And the second,
What's the for exponential separation?
this does no exponential separation here. This is just I prove the entropy increase.
I mean, you are proving.
Yeah, in the final argument, I need to assume entropy exponential separation. Yeah. So up to now, there's no exponential separation. Exponential separation, the gist, the essence is to make sure some active measure, as you can see in the real life case, from the dimension draw, from the separate. Okay, in the statement of I stated you don't need any separation.
Now you apply equation to prove entropy increase with inverse theory. I mean, you are writing applications.
Now I'm explaining the difficulty and how we prove the entropy increase. This is because the entropy from the inverse theorem to entropy increase, it's just a direct counterpassive. Why you should spend so many content to write out the writer? And this is so first is this obstruction. You want to you move this case, and you want to remove this case. This case is that this is the original measure and projected is very full. So let's say this is 1 and this is R2. No, sorry. Still you need this. Yeah, still you need this. But so if this V is the full, then this is 2 minus epsilon and this. Okay. Now I'm focusing according to what VI is. If VI is 0, is this a phenomenon? If VI is a real projection line, is this phenomenon, and this can be proved by projection. There's a to no separation, so actually no separation. This is the saturation over here is the upper bound, so I want to lower bound. V in RP, PV, theta, I, the M is greater than. So this move here and -1 and plus epsilon plus is okay for M. If this base measure, because in our application, this should be base measure, should be some single measure or some conformal measure, some single measure. So this will have approximately to dimension of mu. So this is we want to prove -1 plus some delta or some epsilon 0 depending use that epsilon 0 depending on epsilon. Okay, this is the goal to remove this situation. The third situation is by proving so VI, if it is R2 or C, I want to show that, so there's no low bound by infiniment at all. This is just a PV complement.
You're assuming that another four dimension, other two dimension. You're assuming here is not a four dimension.
I want to explain clearly that PV, that's commons. Okay, I want to explain clearly for my pictures. Because if VI is a plane, what do you mean by the foliation? Foliation is just one atom, the plane. So you don't have to. So if a measure is a plane, you consider conditional on the plane. It's just original measure. So original measure is saturation, which means original measure dimension is the full. I want to know full dimension, which means the original measure, the entropy is less than the full entropy. So there's no V here. Theta actually in here this is some mu. So in application, this is active measure. Active measure will always be the atom, the
acting on the sign, still new is acting the solution. That you actually use. And when you're using, you need a new acting sign. Or just
that's what you want to say, right?
that's
Yeah. But I want to explain ideas. I told you this is some innocent distortion. There's some cosine, you get freedom. I explained more than 3 times, right, for this question. So this is a basic phenomenon you want to destroy, and this is you can get it from dimension 12. That is the active measure. This is some I explained in a special case, and the particle entropy, and then remove this case, and this case is this case. So. And this is called entropy no saturation because it's the opposite of this condition, no saturation, and this is the so-called entropy porosity, and this can be proved by proving the uniform entropy and dimension, a uniform entropy dimension plus dimension not full, and the key of this is a concavity of entropy, and you do not assign mass to the partition lines. This component are this diagonal component, but you want convenient information for the linear measures, and then you prove this mass are very small in plane. In the line, it's very easy by the formula law. You have a positive approximate exponent in a plane without any separation condition. You have to prove this line has 0 mass. Then you can transform using concavity to get this each single part. You have an entropy low bound. Then by zoom out, you can get many components have a low bound by the dimension, and then by local global. The average is the dimension, and then by Markov inequality, you get this mu is a uniform entropy dimension, and then plus our assumption is not full, then this phenomenon cannot happen. And this is deduced from exponential separation plus Ariel's Taylor approximation, and this part is the entropy no separation. You want to get this epsilon for every projection is positive with respect to no trivial low bound, And the strategy is due to I also joined the work with Hausdorff, and but the difference is that in this case, your curve, your maps. Your maps are higher generated, not just Mobius map. It's analytical functions. They are more relaxable than Mobius transformation, but still rigid as Ismail mentioned. If two analytical map or homomorphic map coincide on a set with a accumulation point, then the coincide in the whole domain. Is one utility phenomenon. The other is the competitive Montel theorem. In some sense, that part has already been used in this situation, and the strategy is that you get many direction component. You got distribute all low bound is very easier. Then what you want to get is a positive proportion. You have a non-trivial low bound by this. Mu, this is strictly bigger than mu minus 1 plus foundation. So this is how to get this. Awesome.
Minus 10 minutes.
Sorry. This is that if you these two spaces has a positive angle, then you can get this non-trivial low bound. So then you want to prove some kind of direction reach. Then this can be reduced to the direction cocycle is not co-boundary. Then to make sure two direction is very close in order to have it. That's the gist. Okay. Thank you.
All right, given that we also have some online questions, if you have a quick question, some of them now.
I have a question. Alexei has a paper says something like if it's essentially nonlinear, can you use a Paris scale for dark particle theory? Can be used to study the second conditions out? I mean,
Can you repeat the question again clearly?
Alexei has a paper about the projection these years. He have a condition called essentially nonlinear, and he basically says that no contribution to a self-similar can use it to study the second part of your condition of the projection part. I mean the second.
You mean the talk that Alexei gave in Pokero?
Yeah.
You read the abstract, right?
Yeah, I mean he has a paper. I didn't go to the talk, but he has a paper about.
Yeah. In his paper, it's very nice result, and one condition for him is that the group is this linear part and this considerate part. This condition is so this is the linear part. This is the rotation part and considerate part. Its assumption is this rotation part plus the ratio part together generate a very dense, very large group. But for us now, the only direction matters. I'm not sure how to apply that, but I'm quite interested of a paper of Amir, Federico, João, this maybe. Yeah. Maybe that can be, I'm not sure. Yeah. That paper mentioned of course. Yeah.
Let's thank Joe again.
Yeah.